The next section is a return to the study of motion. We talked about the position function in the past, and so when you have the position function, if you take the derivative of the position function, you get velocity. So x of t would tell you where you are at a given time on the x-axis. The derivative of that would be the velocity. And we also talked about how the sign of velocity tells you whether you're going forwards or backwards. And then the second derivative of your position would be your acceleration. And that's the first part of motion. But the second part of motion, now that we know integrals, is going from velocity to a position. So first I have some definitions. The first definition is displacement. So you have a particle moving along the x-axis, and at t equals 0, it's at -6, and then it moves to the right. So at t equals 3, it's at +6, and then it moves to the left. So at t equals 5, it's at -1. And displacement is just the net change in position over time. So at t equals 5, it's at -1. At t equals 0, it's at -6. So you subtract and you figure out that the net change in position over time is 5 units. You kind of ignore the fact that it took a little detour and stopped at x equals 6 because that wasn't part of the net change in position. Total distance gives you credit for all of the motion. So for total distance, we pay attention to the forward motion. So we went forward 12 units from -6 to 6. And then we went backwards 7 units from +6 to -1. And so our total distance would be the 12 units forwards plus the 7 units backwards for 19 distance. Distance can't be negative. Because it's not directional, it's just how far did you go. So we take all of our distance and we add forward and backward distance together. So in calculus, sometimes you'll be given the velocity function and you'll be asked to find the displacement or the total distance from that velocity function. So first, a definition: displacement. One way to find the displacement is to subtract your ending position from your starting position. And because position is one antiderivative of velocity, using fundamental theorem of calculus, that definite integral is really telling you displacement. If you take the definite integral of the velocity function, you get the displacement, not the total distance, because it just takes your ending position minus your starting position. It doesn't account for any motion that is not part of that subtraction, but it's the net change in your distance. So the definite integral is really about the net change in amount, and that's displacement. If you have a calculator and you want to find total distance, the fastest way to find total distance on a calculator is to just make your whole velocity function positive by putting absolute value bars around it. So for example, here's a velocity function. It starts out below the x-axis, so your particle is moving backwards. And so if you took the integral, you'd be finding, I need a different color. If you took the integral, you'd be finding this area and it would be negative. And then you would find this area and it would be positive. And so you would have a net change in distance. But you don't want that for total distance. You want the actual total distance. So what you do to make it so that you don't have to worry about backwards or forwards is you change your velocity function so that it's just always above the x-axis. And then now the area beneath this curve, all of this area is going to be distance, and it's always going to be positive whether you're going backwards or forwards. So the integral of speed tells you total distance. The integral of velocity tells you displacement. So here's an example of a calculator kind of question. The velocity of a particle moving along the x-axis is given by v of t equals t squared minus 8 over t plus 1 squared. At t equals 0, the particle is at x equals 9. Where is the particle at t equals 5? So it looks like the two times we care about are 0 and 5. So displacement would be x of 5 minus x of 0. And so displacement is also going to be the integral from 0 to 5 of the velocity function. And so if I could figure out this integral, and I have a calculator, so I can, if I can just figure out this integral, that can help me figure out what x of 5 is, because I know what x of 0 is. X of 0 is 9. So I'm going to solve for x of 5, but I'm going to take this integral on my calculator. So I have that function defined on my calculator as v of t. So I'm going to go menu, calculus. Oops, I accidentally hit it twice. Menu, calculus, and I did it again. Numerical integral. And I'm going to go from 0 to 5 of v of t dt. And it's 35, which means that the displacement was 35. And so since our starting position was 9, that means that our ending position was 44. All right. Same velocity function, still moving along the x-axis. At t equals 0, the particle's at x equals 9, still. How far did the particle travel in the first 5 seconds? So now, how far, that's going to be a total distance question. So with a calculator, the easiest way to do this is to go from 0 to 5 of the speed function. So we're going to take the absolute value of that velocity function and do that integral. That's going to account for any backwards or forwards motion. It's going to make it all just distance. So when I do that on my calculator, I'm going to do menu, calculus, numerical integral, 0 to 5. And then the way I can get, the fastest way for me to get absolute value is to just type ABS, parentheses, and then V of t, dt. And it looks like my total distance is 42.587. So that's the fastest way to do total distance if you have a calculator. If you have no calculator, then it's actually quite a process. In order to do total distance, you need to factor your velocity function to find the zeros. Then you're going to integrate your positive distance, and you're going to integrate to figure out your backwards distance. And this might be more than 2 integrals, depending on how your function is. So like if your velocity function looks like this, you might be doing a whole bunch of integrals. And then you're going to add your forward and your backward distance to get your total distance. So we'll do an example of that. Particle moves along the x-axis so that its velocity is given by the velocity function v of t equals t squared minus 1. How far does it travel in the first 3 seconds? So the first thing I want to do is factor that velocity function. It's a difference of 2 squares, so that'd be t plus 1 times t minus 1. And so it looks like I have a 0 at t equals negative 1 and t equals 1, but I'm not going to use t equals negative 1 because we're talking about the first 3 seconds, so we're going to start at 0. So I'm going to do the integral from 0 to 1 of the velocity function, which is t squared minus 1. And I'm going to figure out how far that is. So that antiderivative would be t cubed over 3 minus t, and I'm going from 0 to 1. So it would be 1/3 minus 1 minus 0. So the particle starts out going backwards 2/3 units. That's supposed to be a thirds. Okay. So it goes backwards 2/3 units, but its backwards distance would be 2/3 distance, because distance can't be negative. And then we're going to do the integral from 1 to 3, and this would be forward motion, I assume, but let's figure it out. So that'd be 27 divided by 3, which is 9, minus 3, and then minus, well, we already know if I plug 1 in, I get negative 2/3. So that'd be 6 and 2/3. So the particle moves forward 6 and 2/3 units. So the total distance traveled would be 7 1/3 total distance. Right. Just a word at the end about average rate. It gets confusing because we have average value of a function, but we also have average rate of change of a function. So if I have the velocity function and I'm looking for the average velocity, well, that's going to be the average value of the function. So that's going to be the 1 over b minus a times the integral of the velocity function. But if I have the position function, average velocity would be the slope of the position function. So average velocity would be x of b minus x of a over b minus a. So it's going to be the slope. So pay attention when you see the words average velocity, because it might be that you have a velocity function, in which case you want the average value, or it might be that you have a position function, in which case you want to find the slope. All right, that is motion with integrals. Talk to you later.